Good morning. In this AP Biology video on the immune system, we'll be looking at viral infections, how our body deals with that. And we'll be looking specifically at SARS CoV-2. I've also heard it pronounced SARS CoV-2, but more recently I've heard CoV-2 more often, so that's how I'll say it. And also HIV, the cause of AIDS. And also in this video, we'll look at how a cell is supposed to deal with cancer. Mutations happen, the cell might start to grow out of control, but our immune system can actually have a role in stopping that. The previous couple of videos, we looked at just sort of general, non-specific immunity, skin, interferon, macrophages, stuff like that. In the second video, we started looking at what happens if we are encountering bacteria, so how macrophage might gobble up a bacterium. That's non-specific defense, innate defense. But then we eventually get people involved like helper T cells and B cells, and that's specific immunity or adaptive immunity. And so we've kind of gone through bacterial infection. Now we'll look at viral infection and cancer. A couple of announcements real quick. When we're done with this video, the next videos that we would watch, even though this is the AP class, is Pre-AP Immune 3 and Pre-AP Immune 4. And that would finish up our immune unit. The Pre-AP videos are, like these two right here, are taught at AP Biology level. Pre-AP Immune 1 and Immune 2, those are like watered down AP Bio. So everything that we've done up until now is a full strength version. And in their videos 1 and 2, that combined for like 45 or 50 minutes or something like that to explain the immune system. We are explaining the immune system over 3 videos. When you get to Pre-AP Immune 3, that one describes a lot of the stuff you've seen in the headlines about SARS CoV-2. So is it airborne? What's the difference between being airborne with droplets or an aerosol, for example? And then Pre-AP Immune 4 is about how we would treat SARS CoV-2. So we've got about 4 methods, 5 if you want to count soap. We've got 4 methods that we are thinking about using to treat SARS CoV-2. 4 novel methods, like one's a pretty traditional vaccine and then 3 are kind of unique. So that's what the 4th video is about. Also, don't forget, if you're wanting some review free response still, that's still in Canvas. Go to Files, and then it'll be like AP Biology syllabus. So it'll look like this. I go to Canvas, I go over here to Files. When I click Files, this right here says AP Biology syllabus starting, looks like March 30th. And I update that once a week. So don't forget to go there. And on our YouTube channel, that's where you'll be able to find Pre-AP 3 and 4. So I've got different playlists. If you go into the Pre-AP Bio playlist, then you can see those. Okay, enough with announcements. Let's go back and look at this. This is a now famous picture of SARS CoV-2, National Institute of Health, or the WHO or the CDC made this, but this is the one that you see all over the news. And we hear a lot about the spike proteins, the red proteins. If you can't see it on this one, you can go online and see if there's also some little orange guys and some yellow guys. So that's what I've got over here. So this is SARS CoV-2, the cause of COVID-19, coronavirus 2019. And with viruses, all you have to have, you might remember, all you are required to have if you're a virus is some genetic material and a protein coat. So a lot of viruses also have an envelope as well, though. So for example, this guy right here, he has RNA. The purple, I don't know how well you can tell that it's purple, but these circles are the protein coat. If we go and we look at another picture, we can kind of zoom in and see the RNA inside is yellow and those little red things are the protein coat. And then on the outside of that, we have an envelope. The envelope is made out of phospholipid bilayer, and it's made out of phospholipid bilayer because it came from the cell that it infected. So we'll see that in just a second. Just for accuracy, I put these other proteins on here as well. I've got them as orange and green, but the ones we really care about are the ones that you've heard a lot about, the spike protein. So with SARS CoV-2, it happens to infect a type of lung cell called a type 2 pneumocyte. Type 1 pneumocytes, pneumo means lung, that's why you can have like pneumonia. And so the type 1 cells are the ones that make the alveoli, the lung sacs that basically help with gas exchange. O2 in, CO2 out. Type 2 makes surfactant, and we talk about surfactant in the pre-AP videos, so I'll leave that for those. So this is a surfactant making cell which breaks hydrogen bonds. And this spike protein grabs onto ACE2. That's the original protein that it grabs onto. So cells that express ACE2 are possibly infected. We know that these cells can be infected. There was a study that came out about 5 days ago. Today is April the 28th. There was a study that came out about 4 or 5 days ago saying that our nasal passageways, mucous membrane cells, also express an abundance of ACE2. So mucous membranes would be like mucus making. The snotty ones, you even have them in your eyes, like eye boogers, really are boogers. That really is mucus. When you go like this, that's you're picking your nose, but you're picking your eye. So they might also infect there as well. And then there's this other protein. Let me pull up this picture called TMPRSS2. I wrote it over here so I wouldn't forget, but I've also got it on the screen. And essentially what happens is this spike protein grabs ACE2, and then with the help of TMPRSS2, that's what it helps to use to grab and pull itself in. And these two fit, that's why it infects lung cells. SARS CoV-2, to our knowledge at the moment, can't infect helper T cells because helper T cells don't express ACE2, for example. Now, if we research it, we might find out that they do express ACE2. It's an angiotensin converting enzyme. I don't know if helper T cells would need that for any reason or not. Let's say that they don't have it. That would be why this can't infect this. Flu, for example, can't infect my helper T cells because the receptor that flu grabs onto to pull itself inside is absent from helper T cells. Okay, so hold that thought. This virus over here is HIV. So here's HIV, and it has GP120, glycoprotein 120. So we don't call it spike, we call it glycoprotein 120. This spike protein is also a glycoprotein. They just called it spike and it stuck. And so its GP120 will grab on here to CD4. In fact, I want to double check, but I want to say that this is broken down into two pieces. So there's like the long part and this part. It might be this edge is the 120. So I might have to, I don't really want to reshoot the video, but I want to say it breaks into like a 120 and a 60 or something like that is the breakdown of it. So it turns out with these guys, with the glycoprotein for HIV, it grabs on to CD4. You might remember CD4 from our previous video is held by helper T cells. There's some other cells that we don't even talk about here, dendritic cells, for example, that are also CD4 cells. So those can also be invaded by HIV. We're going to focus on HIV invading helper T cells though. So that CD4 protein is what HIV grabs onto. Then it has this other protein called CCR5 that helps it to pull itself inside. So when HIV is going to invade your cells, it does so by grabbing and then pulling itself inside. That's a more complicated version. So right here, what we're going to do is zoom in. Here's HIV, and here's just one arm. So that one arm is this one arm. So the rectangle and the circle is the kind of cylinder and the circle, and that circle is GP120. Okay, good. So GP120 grabs onto CD4, and then this long skinny part right here almost contracts. So it's kind of like I have an arm, and move these out of the way. So it's almost like I have an arm, and I'm cruising along. I can't grab anything. I can't grab anything. I can't grab anything. And then all of a sudden I can grab onto CD4, and this long part kind of contracts like my arm contracting, and then I pull myself into the cell like that. Okay, so they both get inside of a cell, and they do have a few things in common and a few differences. So the reason that I keep coming back to HIV is we've been studying HIV for several decades. HIV/AIDS kind of became a newsworthy thing in about 1981, 1982. So we've got almost 40 years studying this. SARS CoV-2, we've been studying really hard for like a few months, so we don't know as much stuff about it. So that's why I'll kind of bounce back and forth. Okay, so what do they have in common? They're both RNA viruses, but HIV works a little bit differently. HIV is what they call a retrovirus. retrovirus. And the reason they call it that, retro means like looking back. Like if your clothing was retro, that would mean that it was like older. Like if I started wearing 80s looking stuff, we'd call that retro. So it's going backwards. Well, what happens is whenever my helper T cell gets invaded by HIV, here's my helper T cell, then its RNA, let me make my helper T cell slightly bigger, its RNA doesn't just get read as is, it's converted into DNA. So that's kind of backwards. Normally we go from DNA to RNA to protein, transcription, translation. Well, this goes backwards. So that's why they call it a retrovirus. So it'll look a little bit more like this. My cell is invaded by HIV RNA, and then you'll notice these other two proteins, a circle and a square is what I represent them as. One of those is called reverse transcriptase. Reverse transcriptase. ACE, it's an enzyme, and it does reverse transcription. Again, transcription is DNA to RNA, so reverse transcription would be RNA to DNA. So this reverse transcriptase will convert HIV RNA into HIV DNA. Let me make that look a little bit more. I can't draw a double helix sideways. So that's DNA. Reverse transcriptase, so I'll just kind of use that circle there. Reverse transcriptase ran that chemical reaction. Now, this other guy is called integrase. So integrase is kind of devious. So here is the nucleus, and essentially, if I've got my DNA, my helper T cell DNA, then what happens next is with the help of integrase, that DNA is integrated into my helper T cell DNA. Now right there, it looks like I just deleted some DNA. I didn't, I cut and added it in, so really my DNA just got a little bit bigger because I have all my original helper T cell DNA in purple, and then I have my new piece of DNA in brown. The colors might not come through, but I think you can see what happened. So reverse transcriptase does RNA to DNA, integrase shoves that in there. All the diagrams that I remember seeing show RNA being converted into DNA out in the cytoplasm. Obviously for us as AP Bio students, we would have thought it would have happened inside, because out here we would think that some DNase enzymes would destroy it, would destroy this piece of HIV DNA, but apparently not. Maybe there's some sort of chemical tags on there, and now DNases don't recognize it. I'm not sure. Or it could be that diagrams are wrong, but I've seen multiple diagrams like that. So even though it doesn't make sense to me, that does appear to be what happens. Okay, so now this cell can be dormant for long periods of time. So if I get HIV, I could be asymptomatic for years. In fact, in this diagram, you'll notice, if I zoom in maybe one more click, oops, not that far, that for the first, this is in months down here on the x-axis, for the first 9 months, I have very few symptoms. I'm symptom-free. For the next up to 3 years, my symptoms include swollen lymph glands. So I would have swollen lymph glands. Well, I've got swollen lymph glands for about 2/3 of the year due to allergies. So at least I hope it's allergies. Maybe I'm HIV positive. Okay, so it might be years, and during that time, you can still potentially pass it on to people. So asymptomatically, I can pass on HIV, even though I might not have any significant symptoms. My symptoms are mild. Compare that to, say, SARS CoV-2. SARS CoV-2, we think that you might go up to 2 weeks without symptoms. The average was, I think, about 5 days is what we currently believe. But during that time, you can still spread the virus. So that's why it's hard to contain HIV in SARS CoV-2, because I might, let's say this morning, I became HIV positive, and I got SARS CoV-2, and I got Ebola. It's been a crappy morning. Well, with Ebola, I I don't show symptoms for somewhere around 2 to maybe 8 or 10 days, but while I'm asymptomatic, I can't pass it on. So essentially, once the symptoms hit, that's when I can pass it on. But when the symptoms hit, they hit hard and I get sick, and so I quarantine myself. People are careful around me. With HIV, if I get HIV this morning and SARS CoV-2, and I'm out running around tomorrow, then I might be sneezing or coughing SARS CoV-2, and I can pass that on to people potentially. HIV is harder to get because you need like more body fluids, like sex fluids, blood, stuff like that. So a sneeze is not likely to get you HIV. I would dare say we hardly ever say impossible in biology, but at the moment we would say we don't have confirmed cases of a sneeze passing along HIV. So it's as close to impossible as we ever come to saying impossible in biology. SARS-CoV-2, on the other hand, we think that sneezing and coughing might actually be the primary way that we pass it on. As far as passing on droplets versus aerosols and stuff like that, pre-EP Immune Video 3. I promise, the pre-EP immune videos are good. When I shot them, I knew that I would be likely sharing them with you guys in AP Bio as well. So they are good. Okay, so Ebola kind of knocks you out quick once you have symptoms. So this is why it's easier to pass some of these things along. So real quick, if I look at this, asymptomatic transmission, HIV, flu, all these things. Ebola, you pass on once you have symptoms. Now we're looking at how do you pass them along. Ebola, direct contact with body fluids. HIV, same thing. So those are harder to catch. Like you would probably be doing something to where you knew you were in danger of getting those things. Whereas influenza, this is SARS-CoV-1, but SARS-CoV-2 is also airborne. And then vector-borne, like using a mosquito. Real quick, flu. We saw this earlier in the year. But flu is classified as like, let's say H1N1. That's because their glycoproteins on the outside, one is called hemagglutinin, one is called neuraminidase. The hemagglutinin is what helps the flu actually invade the cell, and then the neuraminidase is what helps it to bud off of the cell. We'll be talking about budding in just a second. And we classify the different types. So you might be H1 if you have type 1, N1 if you have type 1, or you might be H2, N3, or whatever. And different versions kind of have different outcomes for patients. Some are milder and some are quite a bit harsh. Okay, so once SARS-CoV-2 gets into my lung cells, it works slightly differently. With SARS-CoV-2, it has an RNA-dependent RNA polymerase. So we learned about RNA polymerases. They convert DNA into RNA. This is an RNA-dependent RNA polymerase. So it depends on RNA. It reads RNA and makes more copies of RNA. And then that RNA, of course, says, make all these various proteins that are sticking out of the surface here. And so now we'll also start building all these orange proteins and the purple ones and the spike proteins that we hear so much about. This cell has now become a virus factory. HIV will do something similar. It'll start becoming a virus factory too. And then we'll send these proteins up to the surface of the cell. So like, there's a spike, then I have some of the orange guys, some of the purple guys. And from there, I'll start building proteins and putting it on the RNA like this. I'm basically building all the pieces of a virus, and then the virus is going to bud from there. So eventually, my type 2 pneumocyte, a lung cell, is eventually going to start budding out these viruses. So it'll look something like this. Again, I need my Bob Ross little palette of Expo pens. And then here in the middle, I've got my proteins surrounding my piece of RNA, and this lung cell is now budding. It's actually like that's going to pinch off and become the next virus. So that's what we mean when we say it's going to be a virus factory. Why does this matter? In Pre-P Bioimmune video 4, we're going to talk about some ways where like we have some soluble versions of ACE2 to combat this. We have some chemicals that interfere with this RNA-dependent RNA polymerase to kind of screw with this. The whole idea is anytime you come up with some sort of chemical compound that can fight a virus, you want to find something that virus has that our cells don't. Our cells don't use RNA-dependent RNA polymerase, and that's critical for SARS CoV-2 to be able to reproduce. So if I can come up with a drug that basically wrecks RNA-dependent RNA polymerase, it will screw over SARS CoV-2, and it should have no impact on my cells because my cells don't use RNA-dependent RNA polymerase. So that video right there will explain some of those, which is really cool. Okay, so what's a cell to do then? Let me pause and check my time. Guess I'm at 20, so I got about 20 more maybe. So at 12:30. Need to be wrapping up. So what's a cell to do? Let's say that one of my lung cells or something like that is infected. So what a lung cell is supposed to do is use its MHC1. So here's a self cell, like my lung cell. We're going to skip HIV for now on and just focus on this picture up here. On my self cell, I have MHC1. You might remember MHC2. The job of MHC2 was to present what he's been eating. It's called antigen presentation. So from the previous video, a macrophage has MHC2. He'll eat a bacterium, he'll engulf it, lysosomes will start digesting that bacteria, his MHC2 will migrate from the surface of the cell into the phagosome, grab a piece of the bacteria, hold it out there for the world to see. So he's basically going, again, like that analogy I gave. No, it never gets old, does it? He basically says, hey, here's what I ate, everybody. Here's a little piece of what I ate. So be on the lookout for something with this color orange. Well, my self cells are going to do the exact same thing, except they're going to use MHC2. I'm sorry, MHC1. He's using MHC2. They're going to use MHC1. So on my self cell, in this case, a lung cell, what I'm going to do is, I'm going to erase that, I need that space. What I'm going to do is on my MHC1, my major histocompatibility complex 1, I'm going to hold out a piece of what I'm infected with. So I might hold out this. I might hold out a bit of that spike protein. So MHC1 is just grabbing random stuff from the cytosol, random proteins, and holding them out there for the world to see. My lung cell is represented by purple. So let's say it grabs, so I'll get rid of these guys. So let's say that he grabs a piece of purple protein that's from the lung cell. Well, if I hold out on one of my MHC1s a piece of purple protein, then basically my immune system is going to check that and be like, that's a Mr. Cotton protein. You're good. So if I'm an MHC1, I'm just, in this room is a cell, I just go into the cell and I just grab random crap and hold it out there. So I grab stuff, I go to the edge of the cell, I hold it for a while, it gets checked, everything's cool, great, that's purple, that's a falcon. That's what we expect, Mr. Cotton's a falcon. So here's another purple protein, cool. But if all of a sudden I go and I grab this, and I hold it out there, my immune system checks it and they're like, that's not Mr. Cotton, that's some foreign protein. You must be infected. So you're either infected by a virus, or maybe you have some sort of cancer, and so you're making these bizarre proteins that are abnormal. And so an MHC1 is a way for me to tell on myself. MHC2 is, hey guys, here's what I've been eating. Yes, this is a bad guy, but it's my job to like grab a bad guy, eat him, and then show you a piece of it. My self cells are not in the business of eating bad guys. My self cells, when they are displaying something on their MHC1, is saying, hey, I'm invaded, you should probably kill me. And so who is it that can talk to MHC1s? Cytotoxic T cells have a CD8 protein. And CD8 proteins can link up with MHC1. Remember how I told you if you were taking a test on this, you'd want to write down this chart before you start an essay or something? CD8 and MHC1s go together. In a previous video, we saw that CD4s and MHC2s go together. So macrophages can use MHC2 to tell helper T cells, with the help of CD4, what they've been eating. Well now, MHC1 can communicate to cytotoxic T cells to say, this is what I'm invaded with. And these guys are called cytotoxic T cells. So they are cyto, cell, and then toxic, so they kill cells. So this guy will have a receptor, by chance, that matches up, and he'll be like, yeah, you're probably infected with the virus, so we're going to have to kill you. These three steps will seem familiar from NK cells. So we can secrete perforin. Proteins, IN and EN are proteins. ACE is a protein that's an enzyme that make perforation, so it basically blows holes. He can secrete lymphotoxins, so basically harmful chemicals. And he can also secrete chemicals that go into the nucleus of the cell and turn on apoptosis and tell the cell to kill itself. Now, why would I do that? Well, this is a virus factory. So if I stay alive, I might keep producing viruses. If I get infected, let's say I make 3 or 4 viruses, and then I kill myself, then at worst, I'm going to release 3 or 4 viruses. But if I get infected and I stay infected day after day after day, I might release thousands of viruses because I'm a virus factory. So it'd be better for this cell to kill itself. Not me, the organism, but this cell to kill itself. Same thing happens with cancer. With cancer, there are proteins that will sometimes seem abnormal. They'll end up on MHC1. Cytotoxic T cells will say, that is not a normal Mr. Cotton protein, I don't recognize it. Same result, we kill the cell. So MHC1 is a way for a cell to tell on itself, you should kill me, I'm sick. Versus MHC2 is, yeah, I've got the bad guy. Sort of like if I'm a cop and I've got a bad guy in tow, it's like, hey everybody, I've got a bad guy, but don't shoot me, like I'm just doing my job. Whereas if I'm infected with a bad guy, then now I'm basically sending a message that says like, hey, you ought to kill me because I'm a virus factory now. Okay, back to NK cells, natural killer cells. What they do is they go around and they check your self cells to see if you have MHC1. Here's why. This is super clever on the part of the virus. HIV is known to do this. HIV in a lot of successful cancers, bad for us but successful for the cancer. HIV in a lot of successful cancers, what they'll do is they will downregulate MHC1. So I don't know the numbers. Let's say a typical self cell has, 1,000 MHC1 proteins on its surface. You might Google it and find out I'm way off. It might be millions, it might be 10, but I know it's not 1. So let's say it's 1,000. Well, what if a virus like HIV or the cancer, one of the things that it did was if it basically downregulated MHC1, it didn't allow the self cell to tell on itself. So now, this self cell that's sick, instead of having 1,000 MHC1s, maybe there's only 5. So it's gone down 99.5%. Okay, well if I roll up on a self cell and there's only 5 MHCs, now it's much less likely that MHC is holding the harmful protein compared to the self protein. So we're less likely to catch it. However, if I roll up on a cell with only 5 MHCs and it's supposed to have 1,000, isn't that suspicious? It is. So NK cells check primarily for, do you have an adequate number of MHC1s? And if you don't, it'll just kill the cell anyway. It'll just be like, something bad's going on. Use these 3 methods. The analogy I use every year sounds a little bit brutal. But let's say that you drive by a high security prison every day on your way to work. You live here, your job is here, there's a big prison right here. It's an unpopular neighborhood. And so as you drive by, every time you drive by, there's guard towers, there's like 5 guard towers, and there's always like 3 dudes up there in every guard tower. So 15, 3 times 5. And they've always got like M16, rifles, and they're like walking around, they look legit. And then on the floor, down on the ground, you see guys walking around and patrolling. And again, they've got guns. Okay, so you see that day after day after day. Every once in a while, instead of seeing 4 guards on the outside patrolling the ground, you see 3, but you still always see these full guard towers. Then one day you drive by, guard tower's empty. Nobody's patrolling around the outside. What's going on? Is that normal? Or is there a possibility that the prisoners have taken over, right? So what do? You don't ask questions, you're just like, that ain't right, and you just blow the place up. That, I'm not saying you should actually do this, that is the philosophy of NK cells. NK cells, they go and they check your normal self cells and they're like, why aren't the people that are supposed to be telling us what's inside telling us what's inside? And they're like, we're not going to tell you. All right, we're just going to assume the worst and blow you up, right? So that's what NK cells do. That's why earlier in the notes, we even have NK cells as kind of or cancer as a failure of NK cells to do their jobs. Successful cancers do the same thing. You might also remember from our first video on non-specific immunity that interferons upregulated MHC1. So one of the ways that interferons helps is if this cell is sick and I zap it with interferon, that will now upregulate MHC1, making it easier for this cell to tell on itself, which is pretty crazy. Let's see if there's anything else. Vaccines, I cover in these videos, but I can give you a really quick version of a vaccine. With, say, the flu vaccine, I can either pretend that this was flu, I can destroy it. I can't kill it because it's not alive, but I can destroy it and just give you the bits. And now you'll go through the processes that we talked about previously, and you'll make B cells and antibodies. B cells will convert into plasma cells and secrete antibodies and everything else. I could just manufacture this spike protein, inject it into you. Your body would now learn to deal with that. So if you ever get hit with the real SARS CoV-2, maybe you already have memory cells and antibodies built up. Feel like there was something, I'm sure as soon as I shut off the video, I will remember something that I wanted to mention. So we have gotten much better about dealing with HIV. I did want to show you this picture. This process right here where we send the proteins to the surface and then the virus kind of buds, that's what we're looking at right now. So here are these proteins on the surface. This is an electron micrograph. So those are HIV proteins. And then as we move along here, you'll see the virus is starting to bud. And as it buds, you can see right here, this is the original cell, like maybe a helper T cell or a dendritic cell or something. It's taking what we just call the envelope. It's taking some of the phospholipid bilayer with it. That's a pretty good disguise. It's almost like if I was a bad guy and I killed a Timber Creek Talon, then basically what I could do is, or I could overtake him, and I could sort of like, whenever I bud out from him, I take some of the purple jersey with me. It's kind of like you're a bad guy, you kill the guards, and then you put on the guards' clothes as a disguise. So I'm kind of taking a disguise with me. And then in the final picture, we can see as it's almost completely done budding away from the cell. Here's another picture of HIV. You can kind of see that weird sort of capsid protein shape in there. And we have had one confirmed case where a person, scientists agree, yes, he was HIV positive, and they now agree that no, he's not. He was a German guy, and so he's called the Berlin patient, or maybe it happened in Germany. Anyway, he's called the Berlin patient, Berlin being related to Germany. And so you can Google that, and I want to say, I'd have to look it up now, but he's been HIV-free for somewhere along the lines of like a decade. They did a bone marrow transplant, and they haven't successfully been able to do it again until recently again. I'd have to look at it, but I think there might be a second patient that they believe they might have cured of HIV. So we have one and possibly a second person that was HIV positive that we've now made HIV free. However, when you consider how many people in the world have it, then that kind of, I don't know, takes the wind out of your sails. So the dark red places like this lower part of Africa, southern Africa, 15 to 34% of adults are HIV positive. Here in the US, for example, this kind of yellow color, that's 0.5% to 1%. So in the US, somewhere between 0.5% and 1% of adults, I'm assuming they define adults, as we typically do in the US, as 18 and up. So between 1 in 200 and 1 in 100 of adults are HIV positive. Fortunately, we have drugs that can kind of treat the symptoms. We don't really get rid of HIV yet, but we can treat the symptoms and extend your life to where you could conceivably live like to like old age, 70s, 80s, whatever. It used to be that you got HIV, once you had symptoms, everybody was dead within less than a decade. No exceptions. Everybody died within a decade. All right, we will stop there. Make sure you check out these videos. Make sure you check out Canvas. And thanks for hanging out for the Immune Unit.